So before concluding with this section, let's go through one last property of electromagnetic waves, which is more broadly not just their property due to Maxwell's equations, but due to something known as special relativity, and simply the fact that electromagnetism is a relativistic theory. But without going deeper into that, we're going to consider what is known as a Doppler effect. And so this effect is not caused, as I said, by intrinsic properties of the electromagnetic waves as solutions to Maxwell's equations, but by kinematic properties, so by the fact of what happens to movement and to moving frames. So what is the Doppler effect? The most widely used reference, at least, is with an ambulance passing by you. So you must have noticed in your everyday life that if a car with a siren, an ambulance, maybe a police car, if it passes you by, if it's coming near, while it's moving towards you, the sound seems to have a higher pitch. While as it passes you, all of a sudden the sound changes and it seems to have a lower and lower pitch. And what happens? What is this transition? Well, this transition is due to the Doppler effect applied to sound. So this effect is actually the change or apparent change of frequency of waves due to the motion of the object which is emitting them or receiving them. And so, in a sense, it's a modification of the frequency and wavelength of waves due to the fact that the observer or the emitter is moving one with respect to the other. To picture this, you can look at the slide and actually see what happens if a particle starts moving, a particle which is emitting waves. Now, generally, if you think of spherical waves as being simply spherical wavefronts which are propagating away from the source, then we expect a stationary source to create concentric spheres. So, as soon as the wave is emitted, as soon as we picture a crest or a null of the wave, we can draw a sphere which corresponds to the phase which we're looking at. And so these spheres, looking at the same phases in space, these spheres will form concentric spheres which go upwards with equal distance in between them, and those distances are exactly the wavelengths. Now, what happens if the source starts moving? Well, as the source starts moving, the spheres are slightly offset because one wave is emitted, but by the time the next one is emitted, the source has moved a little, and so the spheres are no longer centered on the source. They're no longer concentric spheres, but each one is slightly offset with respect to the rest. And so if we have a constant velocity, this offset will be a constant, and we're going to see slightly closely packed spheres in front, so slightly smaller wavelength, and slightly larger spheres in the back. So the centers of each sphere will be displaced little by little, and those displacements, they will be equal since the velocity is the same. And so as one wave is emitted and the next one starts being emitted, the source will have always moved the same distance. And what you see as a result is that the objects in front of our emission or our source are going to see the waves with a bit higher frequency, so a bit smaller wavelength, while the observers behind our emitter are going to see them as stretched out, and so their frequency will be lower, their wavelength will be higher. So you remember that frequency times wavelength gives us the speed of the wave, and so if frequency increases, wavelength decreases, and vice versa. And so in this visual representation, you can see exactly this effect with a very simple schematic, but you have, in fact, as I said, experienced this effect with an ambulance passing by you, and this is exactly what happens. So as the vehicle approaches you, the velocity it has is actually with respect to you, you are in front of it, and so the waves traveling, they seem to be traveling a little faster, and so their wavelength becomes a little shorter. It's like they're being squashed since the ambulance is coming towards you, and so the waves get a little squashed and their wavelength is slower. This corresponds to higher frequency and so higher pitch. On the other hand, as soon as the ambulance passes you, now it is receding away from you, and so the waves are a bit stretched. In this sense, they lose power, and in this sense, they become higher wavelength waves. So, how do we describe this? Well, the full treatment involves the special theory of relativity, but since we will not require the full formula, What we can look at is simply the case where the velocity of the observer is much smaller than the velocity or the speed of light. Now, this is the full formula on the left. So the frequency of the observed wave with respect to the frequency of the emitted wave is the following ratio, and you see we have a plus sign on top and a minus sign on the bottom when the source and the observer are approaching each other. So we have something greater than 1 on top and less than 1 on the bottom, so we see that the ratio is larger than 1. So when the source and the observer are approaching each other, the frequency, observed frequency, is higher than the emitted. On the other hand, the opposite thing happens if the two are receding from each other. So if they're moving away from each other, simply the velocity changes sign, and so what we get is the minus on top and the plus on the bottom, and so the observed frequency divided by the emitted frequency is actually less than 1, and so the frequency goes down. Now, these two formulas can easily be expanded, and since we're dealing with orbital velocities which are much less than the speed of light, we can only keep the first term approximation, and this is the formula you see on the right. And so, to a first approximation, the ratio of the frequencies is simply 1 minus the ratio of the velocity with respect to the speed of light. So you see immediately that if the velocity is 0, then there is no change. The two frequencies, the observed and emitted, are exactly the same. But as soon as the velocity starts climbing, the ratio becomes higher and higher. Of course, for everyday applications, even for satellites, this ratio is very small, and so this formula is perfectly good to use. Now, just to give you a quick glance at the effect, to get a feeling of the actual numbers involved, let's consider a frequency of 2.44 gigahertz. So again, our favorite S-band. And let's consider a LEO orbit, so a low Earth orbit satellite, which is emitting at this frequency, for example, for the purpose of communication. Now, what we're going to get on the ground, since in LEO we have about 7.5 kilometers per second, what we're going to see is a slightly distorted frequency, so not the same frequency, but a bit higher, a bit lower, depending on what our velocity is with respect to the source. Now, the worst case would be when the satellite is moving directly away from us or directly towards us, since the Doppler effect we're considering has only longitudinal component. So the worst case scenario is exactly when we have this and when the velocity is at its maximal, and this corresponds to 1 plus or minus, depending on is the satellite moving away from us or towards us, the ratio of the speed with respect to the speed of light. Now this ratio, as you can see, is very low for this relatively high velocity, 7.5 kilometers per second. Still, this speed is nothing compared to the speed of light, and so the ratio is, you can see, just 25 millionth of 1. And so it's a very small ratio, but since we're talking about gigahertz, this small ratio corresponds to a delta ni, or difference in the frequency, of almost 60 kilohertz. Now, we will not go any deeper into what exactly this is going to do to our communication, but it's enough to note that the modulation schemes we're going to consider further along are going to be highly sensitive to small frequency differences. In fact, one of the most frequent ways in which we modulate is going to be frequency modulation, which exactly depends on small differences in the frequency. And so such a delta ni of 60 kilohertz might turn out to be a problem. It might reduce the usability of a signal. And so we see, even though the Doppler effect in absolute terms is very low, for these high frequencies, this can be considerable and it can lead to problems with our communication. Now, there is one more term which is nice to clarify. You might have heard of red and blue shifting, and what does that mean actually? Well, this is just another name for the Doppler effect, which is used mostly in astronomy, and the reason why is because if you look at the wavelength of light, as we're going to see in the next section, you will see that blue has slightly lower wavelength, while red has larger wavelength. So blue is around 300-400 nanometers, while red is around 700 nanometers. And what happens is that when you're moving towards an object, as we recall, the wavelength is getting smaller, and so we say it's blue shifted. While if we're moving away from an object, the wavelengths are getting higher, and so it moves more to the red, more to the higher wavelengths. And in fact, this becomes quite interesting in astronomy, and the way you can consider it is that if there was a green object, so something in between red and blue, and if you were simply being stationary, you would see it as green. But as soon as you started moving towards it fast enough, you will start seeing it blue, because the wavelengths will be getting smaller, and so it will be more tending towards the blue. On the other hand, if you were moving away from it, since the wavelengths will be getting larger, at some point you will start seeing it red, and hence the terms red and blue shifted appear. Now, one important note to make about the Doppler effect is that what we're considering here is only the longitudinal Doppler effect. There is also a transverse component, but since it is very small for our applications, we will not be considering it at all. What is also important to note for real-life applications is that there is also a gravitational redshift or blue shift. And so our scenario considered is not completely right, because in addition to the red or blue shifting due to the velocity of the satellite, there will also be a red or blue shifting due to the fact that Earth's gravity is pulling this light. And so in general, we're going to have an additional effect, but since we only need a brief overview, and since this is the most widely used form, we will not go into any further details. Still, for those who are more interested, you can find additional supplementary material on the page.